Good morning, good afternoon, good evening, depending on wherever you're calling from or wherever you're listening from, watching this after we recorded this. This session is being recorded so that people who cannot join real time can also listen in and get benefited. This is a weekly science review organized by Vetri Labs. Vetri Labs focuses on enabling electrochemical technologies implementation at scale. Today, the session is going to be led by Dr. Ayyappan Ilangovan. Dr. Ayyappan Ilangovan is a research scientist at Vetri Labs. Today's topic is going to be on a durable, inexpensive, and scalable redox flow battery based on iron sulfate and anthraquinone disulfonic acid. Over to you, Dr. Ayyappan.
I hope everyone can see my window.
Yes.
Okay, so yeah, today we'll be discussing about a durable, inexpensive, and scalable redox flow battery based on iron sulfate and anthraquinone disulfonic acid.
Quick one, Ayyappan. We are seeing the split screen.
Okay.
So in display settings, you can say.
I changed it.
Yep, it's good.
So before going into the paper, I would like to give a brief introduction about the redox flow batteries. So the redox flow batteries convert electrical energy into chemical potential energy by means of a reversible electrochemical reaction between two liquid electrolyte solutions contain.
To interrupt again, your video off for now, and then we can do it.
Oh yeah. So redox flow batteries convert electrical energy into chemical potential energy by means of a reversible electrochemical reaction by storing two different electrolyte solutions in an external electrolyte tanks. So you basically have a positive electrolyte analyte or a negative electrolyte catalyte on two different external tanks, and then you pump them using an external pumping and bring it into the electrochemical cell where you extract the chemical energy from the solutions and convert it to an external energy that you can use on other electrical circuits. And what are the advantages of the redox flow batteries? So redox flow batteries has a low levelized cost of storage. So the cost of storage can be calculated just by dividing the sum of the capital over the lifetime of the battery system. So in that way, redox flow batteries has the lowest LCOS, and also it's an easy scalable process. You can enlarge the tank size, you can make the electrochemical cell bigger, and that way you can extract more energy density from that device. And also they have a longer life cycles around like 20 to 25K. And also the refueling is faster. It is a safer system with no harmful emissions. Out of all these advantages, right, apart from this, we also need to focus on the disadvantages of the RFBs. It's basically they have very low energy density, and also their charge and discharge rate is relatively low. So next, there are different types of redox flow batteries. You can basically classify redox flow batteries into like two major categories. One is being classical, where all the reactants and products are in a solution base, and in hybrid, where at least one insoluble reactant or product. And you can further classify them into two different types. The classical one, where same species, like you have on both the anode and cathode, you have the same species. So for example, let's take all vanadium batteries. You have both vanadium species on both half cells. Or else the other one would be different species in half cell, one being iron and chromium on the negative electrode, iron on the positive electrode. Next is hybrid. Here, only one, at least one insoluble reactant being a metal, right? So then it can be like a zinc bromine battery, or both the electrodes you can have metal. So for example, all lead batteries, or we can have metal on one end. So then you'll have like flow batteries with hydrogen anode or an oxygen cathode. So example would be a zinc air battery. And apart from these major types, there are other types of flow batteries, that is flow batteries with non-aqueous electrolyte, or organic flow batteries that involves like organic solutions on like being a catholyte or anolyte. Also, there is semi-solid flow batteries using lithium and other elements. In types of redox flow batteries, there is you can play the major importance to use different redox flow batteries is the cell voltage that you can obtain from these redox flow batteries. So before going into the cell voltage, if you look at the half cell region, you want to choose both two extremes, right? So you get the overall cell voltage to be higher. So these are the common redox species that is used in the redox flow battery, where is all liquid or either one solid and one liquid phase. And above 1.23 volts with respect to SH, you start to have oxygen evolution, and below that you have hydrogen evolution in aqueous solutions, right? So considering this into account, most of the redox flow batteries that is already commercially available or scalable are around around 2 volts. And above that is mostly when you use organic or non-aqueous electrolyte, or when you use semi-solid, including lithium iron phosphate and things like that. So in this paper, they were focused on iron-based flow batteries. So why iron is an attractive battery material? Because it is abundant and it is low cost, and it's also environmentally friendly. Then iron-based compounds has been always used as a positive electrolyte in your redox flow battery. A couple of examples could be a ferrocyanide or a ferricyanide couple, or a ferrocene or ferrocenium couple, or iron phenolphthalein complexes. But what is the issue when you use these? These are not a commonly available iron source, right? So then you have a higher cost, then you won't have a lower LCOS. You will be having a higher cost than what you expected it to be. And there are some iron flow batteries that uses inexpensive iron 2 chloride solution. For example, you have all iron. So you have one iron metal as an anode, and the other way you have a carbon melt as a cathode. Or you have an iron chromium flow battery. Even though they use an inexpensive iron 2 chloride, they face a challenge from the hydrogen evolution at the negative electrode, where it's an iron in case of iron flow battery and chromium in case of the iron chromium flow battery. So in this paper, they have proposed an Iron-AQDS. AQDS is anthraquinone disulfonic acid, or anthraquinol disulfonic acid. So this is the first time they have reported as this combination of Iron-AQDS flow battery. So the iron source they have used is not iron chloride, as we saw in the earlier slide. They have used iron sulfate. So they have obtained iron sulfate from steel plant from the scale removal. So the cost of iron sulfate is around 10 cents per kilogram. And also they have used AQDS. They have obtained AQDS. So then the cost comes around $3 per kilogram. So in this iron flow, AQDS flow battery uses aqueous solution of iron 2+ or iron 3+ sulfate at the positive electrode, and a water-soluble organic redox couple like anthraquinone or anthraquinol disulfonic acid at the negative electrode. So basically, in the positive electrode is based on the interconversion of iron 2 and iron 2+ and iron 3+, and at the negative electrode, you have the AQDS undergoes redox interconversion between the quinone and the hydroquinone forms, and you have proton getting released. So since for the source of proton, they have mixed both the reservoir with 2 molar sulfuric acid, and also on the positive side, a high concentration of 2 molar sulfuric acid ensures that the complexes of iron do not hydrolyze. And also the protons also serve to transport the ionic current across the cell. So if you consider the positive electrode reaction here, Fe2+ gets converted into Fe3+, and you have a cell potential of a half cell potential about 0.77 volts. And in the negative electrode reaction, you have AQDS getting reduced to AQDSH2 from quinone to hydroquinone, and then the half cell potential is about 0.15 volt. So relatively, then overall cell potential is cathode minus anode, which would be 0.62 volts. And all their so for their working electrodes, they used geometrical surface area of 25 centimeters square of a graphite felt electrode, but they modified it by mixing it with 10% of multi-wall carbon nanotubes for increasing the electrical conductivity and also increase the surface area. And so this paper mostly focuses on using how you can change the electrolyte configuration, I mean the cell configuration, and how can you avoid the crossover. Because when you use asymmetric cell configuration, like one side you have completely Fe2 like Fe ion solution, and another side you have the AQDS solution. So that condition, you call it as an asymmetric condition. So where you have each type of the redox couple is separated in a different side. In that case, you always have a crossover from one electrode to the other through the proton exchange membrane, resulting in the fading of the cell's capacity. And why this is an important issue to be considered is because of the diffusion coefficient through this Nafion membrane, because that acts as our proton conductive membrane. So here for the iron sulfate and even with the lower concentration of 0.5 molar or high concentration 1 molar iron sulfate, the diffusion coefficient is around 3.33 into 10 to the power minus 6. Because for the iron solutions, the diffusion coefficient in aqueous solution range between 1 to 5 into 10 to the power minus 6. Since the diffusion coefficient that they have measured across the Nafion 212 membrane is closer to the aqueous solution, there is a high chance that iron is going to get crossover, like diffuse through the membrane and reach the other side. So you're going to have the capacity fading. And that is what they noticed. So when they did the charge discharge capacity, where they recorded the discharge capacity by cycling at 200 milliampere per centimeter square, they saw after like first few cycles, the capacity started to decrease and around before even reaching 50 cycles. And when this, what you can notice from here is, with this system, there is a crossover. And how are they addressing the crossover? Is they're trying to use a different cell configuration by either using a symmetric or a semi-symmetric configuration, which we'll see in the next slide. And in the asymmetric configuration, they have used 1 molar iron sulfate mixed with 2 molar sulfuric acid, and with 200 ml on the positive side, and 1 molar AQDS mixed with 2 molar sulfuric acid with a total volume of 100 ml on the negative side. So then the first approach that they've used to solve the crossover is using a symmetric cell configuration. So in symmetric cell configuration, you have an identical mixture of both iron sulfate and AQDS on the both positive and the negative side. So the solution is 0.6 molar iron sulfate with 0.33 molar AQDS and 2 molar sulfuric acid as a total volume of 150 ml in each of the reservoir. The advantage of using this mixed electrolyte configuration is they have a similar osmotic pressure on both the sides of the cell. So that in that case, it avoids water transport across the cell. However, there is one negative aspect that we need to identify is that increased viscosity of the solutions, because both the redox couples are present in the same solution at very high concentration. So usually you have a mixing tank and then you pump down and then you split them across two different like positive electrode side and negative electrode side. And when you charge, you have Fe2 plus getting converted to Fe3 plus. And we can make sure at the positive electrode during charging only iron 2 plus gets oxidized to iron 3 plus. Because AQDS present on this side cannot be oxidized further at that potential of that positive electrode. At the same time, on the negative electrode during charging, only AQDS is reduced to AQDS H2, and iron 2 cannot be reduced at that potential where you are reducing AQDS. At the same time, during the discharge, the iron 3 is reduced to iron 2 plus at the positive electrode, while the AQDS stays unaffected. And AQDS H2 at the negative electrode is oxidized to AQDS, while the iron 2 remains unchanged. So by doing this, right, when you do like multiple cycles, if there is any imbalance that can arise in the distribution of the ion between two sides, they have said that you can do it by mixing the electrodes and evenly splitting the solutions between the two reservoirs. So on the end of charge, you have Fe3 plus on the positive side and more Fe2 plus on the negative side, but then the Fe2 plus is going to get diffused into the, it's going to get crossover onto the positive side. And so at the end of charge and end of discharge, what you find is there is an excess Fe2 plus on the positive side due to the crossover. And they've also identified that AQDS, since it's a larger molecule, there is no crossover influence from the other components. So all the crossover studies is mostly focused on using iron 2 plus or iron 3 plus. So to record the electrochemical performance, so they did the capacity analysis, right? So they did with the 200 milliampere per centimeter square. And as we saw on the earlier slide, the capacity starts to fade away within a few cycles for the asymmetric configuration. Whereas for the symmetric configuration, you identified that there is no noticeable change in the capacity even after 500 cycles. They predict that the average capacity fade was around like 7.6 into 10 to the power minus 5% per cycle. So at this capacity, they can project a overall capacity decrease of about 1.2% about when they operated for like 10,000 hours. So this high stability capacity values is a proof of the inherent durability of this iron redox flow battery. And also they did some other test where they did the repeated cycling to see if there is any change in the shape of the charge or the discharge curve. But they did not find, and they are kind of identified that it is chemically stable. And as you can see here, the Coulombic efficiency is about 99.63% over 500 cycles, suggesting that the crossover, right? If you have crossover, then the Coulombic efficiency is going to decrease. But with this high crossover tells that the rate of a high Coulombic efficiency tells that the rate of crossover is extremely low. Also, since the diffusion of iron 2 plus through the membrane is higher than that of the iron 3 plus, and AQDS does not cross over, they did this mix and split protocol on the earlier slide, and they said it's not usually needed to reset the imbalance in the concentration of the symmetric cells. Next, the third configuration they took is the semi-symmetric cell configuration. In this, you have a pure iron 2 plus solution on the positive electrolyte, and then you have an equimolar mixture of iron 2 plus and AQDS solution on the negative side. So you have 1 molar iron sulfate and 2 molar sulfuric acid on the positive side, and 1 molar iron sulfate with 2 molar sulfuric acid, and 0.5 molar AQDS on the negative side, and both of them are at 100 ml volume. So when they recorded the discharge capacity, and here they did the cycling at 100 milliampere per centimeter square, which is different than the previous two studies. What they find out was that the capacity fade was about 2.8 into 10 to the power minus 2% per hour. So there is a lower fade with respect to time. Also, they did not detect any crossover of AQDS. And however, the difference in the diffusion coefficient of iron 2 plus in an aqueous solution versus iron 2 plus in the combination of an organic solution like AQDS. Also, the difference in the osmotic pressure between the positive and the negative sides can explain why there is a higher fading rate, because in the symmetric cycling, they didn't see the fading rate, right? And here, semi-symmetric cycle, they do have a fading rate at a higher rate, and these are their they attribute these to all these three different factors. So the difference in the diffusion coefficient can also arise from the higher viscosity of the iron 2 AQDS solution, because you have an organic solution compared to a pure iron 2 plus aqueous solution. And they did they recorded the current voltage performance. So they have so initially I mentioned that they used multi-wall carbon nanotubes on this graphite felt to modify it so that they can have an active surface area 150 times higher when compared to the plain graphite felt electrode. So in this way, you can increase the utilization of the active materials and reduce the ohmic resistance presented by the electrodes. So to kind of identify the contribution of the ohmic resistance, charge transfer resistance, and mass transport resistance, they did the impedance spectroscopy for the 10% Nafion on the multi-wall carbon nanotube with graphite felt, and also 5% Nafion. So when they prepare the electrode, they add Nafion as a binder, right? So they played around with the concentration around 10% and 5%. And with the 10%, they used a thicker membrane, which is a Nafion 117. And with the 5%, they used a thinner membrane. So basically, the ideology is to decrease the amount of Nafion. And what they found out was the charge transfer resistance decreases with increasing the current, and mass transfer resistance contributions do not manifest until the current approaches the limiting current for mass transport, while the ohmic resistance is expected to not change with the current. So as you can see, the overall decrease in the cell volt is largely attributed to the ohmic loss. So they did the ohmic correction, and what you can identify is that there is a small difference between this IR corrected voltage and the open circuit voltage. This is consistent with the low contribution of the charge transfer and mass transfer process to the internal resistance of the cell. As we can see here, the ohmic resistance is higher when you use a 10% Nafion, and it decreases when you use a 5% Nafion. And more information, we can go over this slide, where the ohmic loss is usually arises when you use a thick graphite felt electrode, right? It's a 2 to 3 mm thickness, and also the Nafion 117, which is about 175 microns thick. So while they modified it with multi-ball carbon nanotubes, even though it exhibited a lower resistance compared to the one that you don't have any multi-ball carbon nanotube, they found out that by varying this concentration of Nafion, you can actually optimize the overall resistance. So to verify their impact and the ohmic contribution, so they prepared the electrodes with lower content of the binder, which they add when they make the electrode. So reducing it from 10% to 5%. So the use of 10% Nafion, of course, it was expected to yield a better dispersion of the carbon nanotubes and more accessible area to the reactant flow compared to the 5% Nafion. So this difference was consistent with the differences in the mass transport value. So because mass transport value was higher for the 10% and it was lower for the 5%. But whereas the contribution is very low and it's mostly on the ohmic resistance. So what they identified is when they coupled it with Nafion 117, the felt with 5% binder showed a ohmic resistance of 17 milliohms. So this value is like 6 milliohms lower than when you use Nafion 117 with a 10% binder. Further, what they did is by using a Nafion 212 membrane, which is only 3 times lower thickness, and the ohmic resistance further can be lowered to 13 milliohms. So with this, what these observations suggested that the Nafion binder, being an electronic insulator, right, it prevented the multi-wall carbon nanotubes from being electrically connected to the felt structure, thus increasing the resistance of the electrode. And they did the current voltage performance for using the semi-symmetric cycle instead of symmetric cycling, but they've changed the Nafion 10% to 5%, and also they used a thinner Nafion membrane. And with that, what they found out that initially they had about only 136 milliwatt per centimeter square, and now they have a overall power density of 194 milliwatt per centimeter square. And before, when they used a thicker Nafion membrane at higher concentration, they were able to reach only 840 milliampere per centimeter square. But whereas when they use the lower concentration of Nafion and a thinner membrane, they can reach around like 1.16 ampere per centimeter square. So this, and their attribution is like, you can still reduce this ohmic contribution by actually reducing the thickness of the electrodes, which is about 2 to 3 mm, by using like carbon fiber paper electrodes where it's about microns in thickness, or you can increase the temperature of the cell. So you can, these results suggest that you can achieve a higher power density without compromising the energy efficiency. So it will require further reduction of the ohmic losses in the Iron-AQDS flow battery. And you can also play around with the flow field or the electrode combinations to achieve the greater utilization of the internal surface area of the carbon paper electrodes. And also the inherent stability of the active materials can also be, and then the cell can also be operated at higher temperatures. And regarding the efficiency loss, they identified that when they have a round trip energy efficiency of the symmetric cell was about in the range of 70% to 75% when they have a constant current density of 100 milliampere per centimeter square. And it is 70% of the 70% utilization of the theoretical capacity. And then the Coulombic efficiency of this Iron-AQDS battery was very close to 100%. So that kind of tells that there is a significant reduction in energy efficiency is avoided, whereas it cannot be avoided in the case of vanadium flow batteries. So the overall point when they came to this paper was to have this LCOS target. So the LCOS target for the large scale energy storage system is actually, this is wrong. It's 25 cents per kilowatt hour. And theirs is about only 4 cents per kilowatt hour. And so to consider this, to calculate this LCOS, they've used system specifications, right? So The overall cell voltage, we know it's 0.62, but then, so you assume that's a daily storage of 10 hours and you can cycle them. Daily cycles per year is about 360 cycles. And there is a fixed cost, right? FeSO4 is only 10 cents per kilogram and AQDS is $3 per kilogram. So by considering this and by considering only 80% of efficiency, they obtained it's only like 5 cents per kilowatt hour when you use AQDS battery. And when you compare it with the best redox flow battery, which is our all vanadium flow battery, the drawback is the overall cell voltage, right? So you have a higher cell voltage, which is 1.26 volts versus the vanadium flow battery. Whereas with this, you have only 0.62 volts. So this tells that there will be a maximum that you have to increase the number of stacks to get an overall voltage. So considering all that, they can identify that when you operate it at different voltage level, so your cost at least goes by 2 times. So the conclusion is, so with this, they have used inexpensive Iron-AQDS flow battery and found it to be rechargeable over hundreds of cycles with a very low rate of declination in the capacity. And also they can obtain a Coulombic efficiency of 99.63%. And they can also obtain a higher current density as high as 1.16 amp per centimeter square and a power density as high as 194 milliwatt per centimeter square when they can optimize the cell design. And they were also able to avoid the crossover by changing the cell configuration. And they also reduce the ohmic resistance by about 40% by altering the composition of the naphion and also the carbon nanotube. And the Iron-AQDS battery actually overcomes the challenges you encountered with the other iron flow batteries. Even though you have a lower cell voltage, the durability of this battery combined with its low cost materials has a unique opportunity for further optimization of these electrodes and other configurations to meet this like high mega scale energy storage applications. With that, I'd like to thank you all for listening to this and we can start the discussion.
Thank you, Ayyappan. That was very nice summary. Great. And questions, comments, thoughts?
I had never heard of flow batteries before this paper, and like I didn't know much about it at all. But I think you did a really great job summarizing it, and some of it went over my head. But I think this technology looks to be like super effective, especially because like it doesn't use too many materials, and it's more renewable than like some of the current batteries right now.
Yeah. It's well suited for stationary storage, where you're looking at grid level energy storages. So did they do any studies without the carbon nanotube, Ayyappan?
No, all the studies have been done by using multi-wall carbon nanotubes to just increase the surface area. They have not used just the graphite felt electrode.
Yeah, that's what I was looking at when I was looking at the paper. It would have been good to compare the performance with and without multi-wall carbon nanotube.
Yeah.
That way you really understand the improvement on the activation.
Yeah.
So that would have been a nice control study to present as
Yeah.
part of this paper.
Yeah, true. And also the impact of like maybe different weight percent of or different percent of multi-wall carbon nanotubes, if that is what actually influencing, because their whole study was focused on crossover, so couldn't understand the importance of the multi-wall carbon nanotubes as you mentioned.
Correct, correct. And I did see some differences in the impedance spectroscopy, even though they said they looked similar in terms of the Nafian content.
Okay.
I did see some signature differences, but it needs, again, more control study to understand the mechanisms there.
Yeah, they did kind of mention in their SI because their impedance was in the supplementary. They were not in the main text. And they mentioned that they had some noise at the higher frequency range. So when they kind of made the equivalent circuit for the two different concentration, there was only 10%. I could not see the equivalent circuit for the 5%. So that was kind of missing and did not know how they came up with those numbers at last.
Yeah, understood. Got it. But what I liked about the paper is it's looked at the techno-economic aspects, not just the technical aspect. it's about the practical implementation. So Vetri Labs being focused on implementation, I liked that aspect
Yeah.
of looking at the cost, and 5x reduction that they're projecting is very nice to see. Yeah.
Also, I thought that one thing that could have been better is because I'm not sure when they changed the Nafion percentage and also the membrane, they have switched to semi-symmetric configuration instead of symmetric configuration. So when the 10% was done at symmetric configuration, like having same solution on both the sides, whereas when they reduced the concentration of Nafion to decrease the ohmic resistance, they switched the configuration. So that wasn't clear why they have done that. And also when they used a current density, different current density, so it looks like in the semi-symmetric, you have a higher capacity, but there is a capacity fade is there, whereas in symmetric, you don't see the fade, but the capacity is low. So those kind of questions came up when I was just reading this paper.
Yep. So sort of a balancing act there.
Yeah,
Try to
yeah,
see, do you need high capacity or you need capacity
capacity
stability?
stability. Yeah.
So those are the two things that come up. Yeah. Very nice paper. Thank you. And next week, I think
Yeah.
Mani will be talking about what's the paper. Can we flash
Yeah.
that, please? Yeah.
So next week we'll have my bad, just so next week we'll have the discussion about enhancement in the selectivity and sensitivity of nickel and palladium functionalized MOS2 toxic gas sensors from Journal of Electrochemical Society.
Great. Thank you, Ayyappan. That will be led by Mani, who's currently the Director of Chemical Engineering and Director of Engineering at Plug Power. If any of you would like to lead the discussion, please send an email to info@vetrilabs.com. Thank you for joining us. And that concludes the recorded session.